Okay, so last time what we had discussed about noisy data, right? I mean, how to handle noisy data. Like there are many things which I'll make a separate video by myself, okay? And I'll share it to you during holidays. So no need to worry. It's like there are some tiny functions, like what is a series in pandas, okay? How you can drop duplicates in your data frame. So using drop duplicates, drop NA commands. So those tiny things I will, I think it's a bit difficult to cover now because when you are covering a big syllabus, they appear sometimes, they don't appear, and like that they get missed during the lecture. So this I was planning to cover in the previous lecture, but I think I have to make a separate video by myself and I will share with you. Okay. So those 3 to 4 comments are there, and I will make a separate one for you. Okay? So this lecture we will focus on multiple things. Okay, we'll focus on multiple things. So first is how to handle noisy data. So last class we handled outliers. What is an outlier in your data set? How to find outliers? Okay, how to detect outliers? We saw. Can anyone say how we detect outliers? Z-score and IQ. What is IQ? So Z-score and interquartile range. Okay. So based on that, we detected outliers, and outliers are also like if there is noise in your data, most likely there is a presence of outlier. Okay, because your data set, your data patterns, like the value in your data set has particular pattern in it. Okay, like suppose say like rainfall. We'll see an example: rainfall and humidity, or humidity and temperature. So those two are kind of correlated. So if you want to see that, what you can do is you record those data. What is the temperature today? How much humidity it has today? And record it for 1 month and plot them on X and Y axis. So you'll get a set of points, like a scattered set of points, and you'll see kind of like a pattern. Okay, there is a pattern. Like today it is hot, and tomorrow you possibly like can expect rain, but suddenly it won't happen. Okay, it will just change, the temperatures gradually drop, and suddenly you will see the temperatures dropping, then the rain will come. Okay, so but sometimes weathers are also unpredictable. You cannot predict what happens, like suddenly it might change. But if there is some, the weather patterns and all are being monitored by large computers. Okay, they have large simulations they are running. So if there are some errors in that, you will see that suddenly some other data sets away from those patterns might occur. Okay, those are like outliers, right? So those are kind of noise because they happen due to errors. Okay, so yeah, we already, I think I did not communicate to your class, like errors are always there. You cannot eliminate errors. Can you tell why? Can you give me an example? So if I ask you to draw a 3 centimeter line, if I ask you to draw a 3 centimeter line, can you draw a 3 centimeter? Even during high school days, if your exam asked, like you took a geometry box to your classrooms, so you will take out a scale, start from 0 point, put a sharp pencil and strike it till 3, and that's your line segment 0 to 3, and that's 3 centimeter line segment. Okay, but is it exactly 3? It will never be exactly 3 because there is some width in your pencil, there is some friction in your paper sheet. So therefore you can never reach 3 centimeter. It will always be, maybe it will be 2.999, but the error of 0.001 will still be there. So in this world, however fast you go, you cannot achieve 100%, I mean, error-free calculations or error-free computations. So one just small tiny example is this. So there will be always an error, regardless of how small it is, like 10 to the minus 3, 10 to the minus 5, 6, right? So there will be noise. So there will be noise. Where there is error, there will be noise in your data set. So how to handle those? So like you can see, the first one is a bit non-intuitive. Like it's so therefore I wrote it there. Like you can see, first sort the data, partition them into bins, okay, and then I use the mean, something is there, which is kind of like not understood. And I want it to be like that for the first instance. This method is known as binning. That's what we will learn in this lecture. Okay. Then using regression also, you can smooth out your data set. You can smoothen out. We'll see, just we'll not go into details, but I'll just show you one figure where you can catch the intuition and idea. Okay. So smooth by fitting the data into regression functions. Okay. So next slide will show you that clustering, like detect and remove outliers. Like if you plot the points, you can easily detect outliers. Okay, we'll see that. So let's go. Let's go to the next one. Okay, so what we see in this picture, what we see in this picture. So you can see that here temperature is there, okay, and humidity is there, right? So you can see these data points. Like these you cannot call as regression. Sorry, the outliers, because the distance between them is quite small, and they might not be falling under your category. That is 3 times the standard deviation, what we learned in the previous class, right? So therefore you can see the difference between this point and the regression line is quite big. Okay, and such differences of the regression line and your actual data set is kind of called residual. Okay, it's kind of called residual. Okay, so more about this you will be learning in your next semester. I mean, more detail about regression. Uh, those who are in DSCS might learn in numerical methods about multilayer perceptron, how they are helpful in regression, kind of from a neural network perspective. But next semester you will also learn about logistic regression and stuffs in your predictive analytics course. Okay. So anyway, so this is the outlier. We understood this. This is an outlier. But what role does the regression play here? That's my question. I mean, you can see, like the previous slide I told you, it smoothens out your data, right? It smoothens out your data. You can see the data has a particular pattern right now, right? It has a particular kind of pattern, but then there is a sudden point here which disrupts that pattern, and that is a sudden jump, right? Now you have to smooth out those jumps. How you will smoothen out? You need some, so if you want to smoothen out that point, it has to go from that outlier point to some other point. But where it should go? That's the question. So it can go to a like a well-judged point, right? So only the well-judged line is your regression line, right? So if you can see, instead of this point, you can just draw a vertical line onto the regression line, and this point instead will be considered. This point instead will be considered, right? So if you lose some of your points in your regression, it's a loss, right? So instead of that, maybe you can use this one, right? Which is kind of like in your line on your regression line and a smooth version, because this point lies in the cluster of the pattern, like it follows the same pattern before, right? So in that way you can see regression helps somewhat in your when your data has a noise, when you have a noisy data, or like when you have kind of outliers. So this is just an intuition, just a tiny bit of intuition. More detail in other courses. Also clustering, you can see now this example over here, like, so there are a lot of points here, lot of points, and you can see each we can bound them by clusters. So you can see there are 3 clusters here, C1, C2, C3, right? Now, of course, there might not be any outliers, but you can, of course, if I do a point here, then it is an outlier, right? So by clustering also, you can handle noisy data by just clustering them. How, if you want to understand more about clustering, you can apply something like k-means, okay? So those also you will learn in predictive analytics, right? So just an intuition I'm trying to provide in this one. Okay, now the first option we learned in this is binning here. Binning, what is binning? So binning means like you have to, of course, bin them. Like when you go to different shops, like 2, 3 people, to the malls, what you do, you take your carts out and you start putting stuffs in, right? So that's like binning. You have stored, like maybe you can say like, yes, I want to put all vegetables in one section in one of my carts. All maybe those pulses I can put in another cart, right? So like that you can bin them out. So same logic is applied here. You can use binning. So we'll see what is binning in detail. So it is also known as discretization. So last class, if you remember those, like we told about discretization also. Then I told that we'll cover them. So it's also a kind of discretization here. Um, why it is called discretization also we'll understand. So binning, also known as discretization, is the process of taking a continuous variable, numerical variable, and converting them into discrete variables. Okay. So therefore, you are converting a continuous variable into a discrete set of variables. Therefore, this is known as discretization. Okay. Therefore, it is known as discretization. Also, you group them into bins or intervals, right? So therefore, the term is binning. Okay. And it's a process of discretization because you have a continuous variable and you, by applying binning, you transform them to discrete variables, right? So we'll see an example like maybe we'll see, yeah, the age is there. Like age is a continuous variable actually. You might see as a discrete variable because every year it is increasing by 1, but your age can be 23.4. Your age can be 24.5, right? Like 24 years and 6 months. It can be like that, right? So it can vary continuously. 24 months, 24 years, 6 months, 3 days. Okay, 3 days and 12 hours, 5 minutes, 2 seconds. So it can be like very discrete. Okay, so I'm just trying to give you an example how it can be discrete variable. So now we understood binning. Now let us apply to a very tiny example over here. Like you can see, these are our ages in years. Okay, so 12 years. So you can say this is equals to age equals to this array over here. So what we want to do is we want to bin them. Okay, you want to bin them like this whole class. I want to bin them, right? I want to bin who are teens over here, who are young adults, who are middle aged, like that, right? So you can see over here, like if we apply binning, of course we convert this continuous variable into categorical or discrete variables. Okay, so you can see over here I am classifying this. This is my classification. You can do as per your classification, right? If your age lies in between 0 to 18, I will call them as teen. If it is lying in between 19 to 35, it is young adult, okay? 36 to 60, middle aged. 61 plus, it is senior, okay? So your job for binning would be like you can create bins. Like this is teen, this is young adults, okay? This is middle aged, and this is senior, right? Now, what is your job in your binning is you see where this 12 will fit, where this 12 will fit, right? Where it can fit to the teen. So you put it here, right? So similarly, you go to the next one, 14. Of course, it will fit again here, 14. Then 18, yes, right? Then you go to 23, it will fit here, okay? Then 24, maybe here only. 28 also, 32 also. 40, it will go here. Then 60, yes. 70 it will go here. So you can see that we have carefully divided like the age groups or the people in your age array into different bins. Okay. So depending on this idea, like there are two classification of binning. Okay. One is known as equal width binning, another is equal frequency binning. Okay. So what is equal width? Equal width we'll see, but equal width binning means what your intuition says. The width of each bin should be the same. Equal width binning means the width of each bin will be the same. Okay. Equal frequency binning means number of elements in each bin will be the same. Like number of like frequency of elements in each bin will be almost the same. I mean, you cannot guarantee always it will be the same, but almost the same, right? Almost the same. Like 2 elements, 3 elements, right? Like that. Like you cannot say one element will also be there, 3 elements will be there. Then there is a gap. Okay, so 2 and 3 is kind of okay, but almost similar number of elements. But that you cannot guarantee in equal width binning. In equal width binning, you can only guarantee equal width of your bins, but you cannot guarantee same frequency in each bin. Okay, that's the difference between equal width binning and equal frequency binning. Okay, so that we will see. But you understood by this line, I hope. Each data point is mapped to a category. Okay, so that's the basic idea of binning. Okay. Okay. So why we are using binning? So you can see to make continuous data a lot easier to interpret. Okay. So you can see, let us go to the previous one. When you have this array, it is not very clear. I mean, it's not very clear. Wait a bit. Okay, it was running. Fine. So, yeah. So what I was telling is, what I was telling. Yeah, I was telling, I think the array, right? So you can see the array and you are not getting any idea about it. It's just numbers. It's just numbers. But when you bin them, you are able to tell that yes, in young adults, this data set has lot of people in young adult section. Yes, by binning you can say that. Okay. Otherwise, if you present your data set in this format, you're not able to say. So when you do the binning, so it is the interpretation gets a lot more easier. Okay, the interpretation gets a lot more easier. Pattern detection, of course, you can detect pattern. Okay, you can detect a pattern that yes, you can see after young adults, more number of teens are present in your data set, and least number of seniors are present in the group. So you have to bring in more seniors to make the program more, interesting, something like that. You can get insights. Robustness, of course, it reduces noise, measurement error, and impact of outliers. This we will see. Some machine learning algorithms, like you will learn as you grow, like as you go through the semesters, other semesters, like decision trees, they work better with categorical features, and therefore you use binning, because binning is also a process where you transform a continuous variable to a discrete categorical variable. Okay, so therefore you can see and learn about decision trees, and maybe at that time you will hear the word binning again. Okay, fine. So as I already told you, there are two types of binning. One is equal width binning. Okay, one is the equal width binning over here, and second, I think yes, this is the second one. This is the equal frequency binning, also known as quantile binning. Okay, so you can see it splits the range of values into bins of the same size, right? So what you do is, suppose, for example, if your age ranges from 0 to 100 and you want 5 bins of them. Okay, so in your data set, what is the question? You have age ranging from 0 to 100, right? So age will lie in between them. No variable of age will go above them. No value of age will go above them or below, right? So this is the minimum age and this is the maximum age, right? And equal width binning will depend on the maximum and the minimum parts. Okay, understood? Is it clear? So equal width binning will depend on the maximum and the minimum parts, right? So you can see the effect of outliers here. You can see the effect of outlier the moment I tell you about minimum and maximum, right? So when you have like outliers, it can be a small outlier also, it can be a bigger outlier. So suppose it has a bigger outlier, then your maximum will get affected. So your binning will get affected. So therefore, if there are outliers, you have to carefully choose your binning strategy. Okay, because equal width binning depends on the minimum and the maximum. Okay, and suppose you have a outlier which is of higher value, okay, then it will affect the maximum. That value will be the maximum, okay, which is an outlier. Okay, we'll see. Those who are not understanding will see. But let us see through this example first. You have age range from 0 to 100. So minimum is 0, maximum is 100, and you want 5 bins out of this. So what you do max minus min divided by the number of bins. That is equal to 100 minus 0 by 5. That is equal to 20. So 20 is like 20 years. Okay, this is 100 years minus 0. So 20 years is the bin. 20 years is the bin, is the width of the bin. What does it mean? So you have to bin it like this. In between, so you have to bin 0 to 100 and you know the bin width is 20 years. So how you will bin? You start from 0, add 20 to it. 0 to 20 is one bin, 20 to 40 is another. Okay, maybe I will put this one. Okay, then 40 to 60. Yes, right? So you can see how many bins are there. 1, 2, 3, 4, 5. So I have created 5 bins here. And is it equal width? Yes. Each bin has width of 20. So it's a equal width binning. It's equal width binning. So for equal width binning, you only need to know the maximum value of your data set, minimum value of your data set, and how many bins you want. How many bins you want. That much idea only you need to know. Okay. Suppose I will tell you one example like, okay, let us come. So you can see it is easy and intuitive. And one of the disadvantages is outliers can distort the binning. This I already told you. Outliers can distort the binning. Can you think how? Suppose there is an outlier. Suppose there is an outlier. Like maybe we can take one example of your data set. Can you tell me age data set? 14, 24, 33, 23, 99, 120. Let us not make that. 116. That's the maximum age so far being found today. Okay. So that's the age group. Okay. You can clearly see, okay, 99 maybe can also be thought of as an outlier. Let us make it 49. Okay. 49. So clearly you can see 116 is an outlier here. 116 is an outlier here. So what your binning will do? Your binning will take the maximum, which is 116, and minimum is 14. And how many bins you want? Maybe you can tell. 4. Okay. Can you tell what it is? This will be 102 divided by 4. Of course, it is not getting splitted like 4 to the 8. Then 20. Fine. So 25.5. So how your binning will look like? You start from 14. Then you add 25.5 to it. So what it is? 39.5. Right? Then you take 39.5. Then you add 25.5. Right? So you can do the binning, but can you do, can some of you go with me, like do these calculations? What is this? 25.5 means 65. Then 65 to 90.5. Then 1 1. Are you sure? 1 1? Okay. 116. Okay. So you can see like now can we bin them? So you can see 14 will lie here, right? 14 will lie in this bin. 24 will also lie in this bin, right? 33 will also lie in here. 23 will also lie in here, right? 49 will lie in here. 116 will lie in here. So you can see one of the bin went empty. One of the bin went empty. Okay. So that's a loss because you're creating bins, but bins are going empty. So when you have outliers, you create many bins and many values will fall into one bin. Okay. Many values will fall into one bin, whereas other bins might go empty. So therefore, your outliers can distort binning. That is minimum and maximum stretches the bin. Okay. The minimum and the maximum will stretch the bin, and bins may have very different number of observations. Okay. So you can see this bin, the first bin had 3, 4 observation, whereas other three bins had just one observation, and one bin has 0 observation. So you can see most of the values get concentrated on one bin. Okay, that's kind of a disadvantage. Okay, because some of your bins are going just like with null values, no values. Okay, so this is equal width binning. Okay, I mean this is one example. In Python also we will see how to implement this binning. So there is something known as cut function. Okay, cut function, like in pandas, like what you can do is pd.cut. If you say give your data frame over here, okay, and tell how many number of bins you need to give them in your data set, then it will automatically do this process for you. You don't have to write a specific 3-4 lines code for that, right? Understood? So pd.cut will implement this equal width binning. To implement equal width binning in Python, you can use pd.cut. Okay. Fine. Now let us go to the next one that is known as the equal frequency binning. Okay. So equal frequency binning doesn't care about number of doesn't care about the width of the bins. Is it clear? Like in equal width binning, we were concerned about the width of the bin. So in equal width binning, your width size will be the same. But in equal frequency binning, the number of elements in each bin will be the same, almost the same. That is the idea. It doesn't care about the width of the bins. That's the catch. That's the difference between the equal width binning and equal frequency binning. Okay. So you can see each bin has approximately the same number of observations. So number of observations is nothing but a frequency. How many times it happens within 1 second is like a frequency, right? So therefore, I hope you remember in your physics days that frequency is kind of 1 over time, right? Yes, 2 pi by t, something like that formulas. So it has second inverse unit, right? So how many times it occurs in a particular duration, that is frequency. So how many number of observations are there in each bin, that is a frequency. Okay, let us see an example. Suppose you have 1000 data points and you want 5 bins. Okay, so each bin gets around 200 points. Okay, so you can see there is a balance across balances data across bins. So you can see each bin has almost same amount of data points. Okay, but there is a disadvantage also that the bin ranges may be uneven, which is bit different from equal width. Equal width bin range are the same. Bin range, like we saw, from 14 to 39.5, the difference is 25.5. The width is the same. Here also the width is the same, but here you might not have that. And that's one of the disadvantages. Okay. So if your data is skewed also, it might affect it. So let us see. Here I think I will give you two different examples. Another example, I think again we can go through this. So equal sized interval. I hope that is clear. So just carefully remember the main points of each binning strategy. So in equal width binning, the interval size should be the same. That suppose the interval is a comma b, then b minus a is the interval width, and that should be the same throughout. Throughout all the bins. Throughout all the bins. Okay. So bin edges are evenly spaced regardless how the data is distributed. So this is good for uniformly distributed data. And we saw that if you have an outlier, how it affects. Okay, some of the bins can go empty. So you can see this is the exact example we did. It may lead to empty or sparse bins. So we had one empty or sparse bin in our case, in our example, right? When we took 160 as one of the outliers age, right? If your data is skewed or has outliers, right? We saw one of the examples. So this, I hope this point is clear to many of you. Okay, so again, another example. Suppose you have this data set. How many elements are there? 1, 2, 3, 4, 5. Okay, 5 elements are there and you want 2 bins and you want to perform equal width binning. So what should be your strategy? Find the maximum element. What's the maximum element? What's the minimum element? Okay, then divided by 2 bins. So how much it is? 4.5. So this is your width of the bin, right? So you start from the minimum guy, that is 1, okay, and add 4.5, that is the width to it. So 5.5. Can you see it here? So that is one of the bin. Then second bin is from, yes. So there are 2 bins and you can see like each of the bins have the width size of 4.5. Okay. So you can see first bin has 1, 2, 2, 3. Second bin has 10. But here you see the number of elements in each bin is not almost the same. Number of bins are differing. So the frequency is differing, right? Which won't be the case in the next strategy. Okay. And you can see bins are unevenly filled. That's what we mean. Like the number of elements in each bin is not the same. Okay. Now let us go to the equal frequency binning. Okay, you can see it divides the data so that each bin has almost a similar kind of number of elements. The frequency of elements in each bin is almost the same. Okay, so bin edges depend upon the distribution of your data set. Okay, we'll see an example. Take this example again. 1, 2, 2, 3, 10. Okay, this is an array and you want 2 bins. So what you should do? So first you sort your data 1, 2, 2, 3, 10. okay? And one of your bin, you can put 1, 2, 2, okay? Because 2 is repeating 2 times, okay? And 3 and 10 will fall in another bin, okay? So you can see all there is not the equal number of elements, but technically 1 and 2, 2 is repeating 2 times. So in that way, that sense, you can still feel that there are 2 elements, okay? Number of elements is 3, but 2 is repeating 2 times, okay? Okay. But you can see the bin ranges here. The bin range is different here. It is like 1 to 2, 3 to 10. The bin width here is 1, whereas the bin width here is 10 minus 3, that is 7, which is different, right? So you can see a difference now between this binning strategy and equal width. Okay. I hope that is intuitive. Okay. So let us go to the Python one just to see. Mm, yeah. So is it visible to last page? No, visible. So you can see over here, I have this data set again. And what I am doing, I told you already that we will use cut function. We will use cut function in pandas to perform this equal width binning. Okay, to perform the equal width binning, we will use cut function, pd.cut. And all the strategies how we discussed, that take the maximum, take the minimum, divide by the number of bins, and allot each point of your data set in your bin, comparing, right? So there are some steps, okay? That all these things can be automatically performed by the cut command, right? So pd.cut. You don't have to write a code for that, like max equals to max of your data set, min is equal to min, then divide by the number of bins you want, okay? And then write a for loop and compute each point in your data set and find which bin it will belong, right? There is a process, right? If you want to do it automatically, you have to write a piece of code for that, but you don't have to do. pd.cut can do for you. So you can see this is your data set. So pd.cut data, you are passing this array over here, okay? And bins equals to 4. You want 4 bins. You want 4 bins. So you are claiming that this is my data set and I want 4 bins and I want to perform equal width binning. How are you telling Python that you are performing equal width binning? Because the cut command. Okay, if you do cut command, it means you are trying to perform equal width binning. For equal frequency binning, we have a different command, that is qcut, that is quantile cut. Okay, so equal frequency binning is also referred to as quantile binning. Based on the quantiles, you do it. So therefore, we sorted the data, right? Anyway, so pd.cut, what are the inputs? Data and bins. Okay, I suggest you that you go home and try to understand about this function pd.cut. Try to see what is the syntax of this. Okay, why do you have labels equal to false? Why not labels equal to true? This I leave it to you. Okay, what will happen if you put labels equal to true? I want you to, I mean, do some research on this. Okay, but anyway, when you do pd.cut, the output is actually a series, pandas series. Okay, series, I hope you will learn in your other course, but I will make a separate lecture on that. Okay, so don't worry about it. I came to know that there are some cases we miss these tiny things. Okay, so I thought that we can make a separate one. Okay, like it will come like this. It's a pandas series, like the pd.cut, the output of pd.cut command, that means bins labels width, is a pandas series. Okay, it's not anything else. It's a pandas series, and that series we can print, but the series will have index and like all these things starting from 0, which is not a good way to look into your output. So therefore, we are converting that pandas series to a list. Okay, list in Python, right? So therefore, you see dot to list command here. So it tells that please convert this pandas series, which is bins labels width, to a list. Okay, to a list. So you're here in this line, in the last line over here, you are converting a pandas series to a list. Okay, and you can print. So as a list, it will look like this. If you have a series, it will look something like this. 0 0 like 2 3 3 something is there. So this is index 0, this is index 1 2 3, this is the index, and this is your data. So this will be a series, okay, which is kind of difficult to interpret. So therefore what we did is, please convert that into series using dot to list command. Okay, you can put the name here, you can put the name over here, and it will convert to a list, and you can see the output here. It is this. Fine. So here we asked for 4 equal width bins. Okay, so you can see what is the minimum over here. That's the first thing you have to perform. 7. Yes, minimum is 7. What is the maximum? 49. Okay. So you can see 49 minus 7 divided by the number of bins, which is 4, and you got 10.5, right? So you start from bin 0, that is 7, the minimum element, add 10.5, got 17.5. Okay. So you can see that there is a square bracket and there is a moon bracket. Square bracket means you include that point in the bin. I hope though some things like this very basic, I think. So, and if you have a moon bracket, it means don't include that point. Okay. So you can see bin 0 is 7 to 17.5. So 17.5 is included. So 17.5 is included in here. And bin 1 is 17.5 comma the next one. Okay, that is 28. So 28 is included. And then the next bin, it starts from 28, but 28 is not included. Okay. Yeah. So this is the idea. Then what happens? Then you decide. So this is up to here. Then what you do after creating the bins? What you do? You assign each point of your data to the bins. You assign each point of your data set to the bins, right? Agree? So that we are doing manually now. Right now, right? So what you can see, 7 and 15 will lie in the bin 0. These will lie in bin 1 or 2 depending on your boundary, like 36, 39, 40. 36, 39, 40. 36, 39, why I wrote like this? 36 will fall into bin 2, okay? Don't worry about it. 36 will fall into bin 2. 39 will fall into bin 3 and all others in bin 3. Fine. So that's the idea over here. So you can see the piece of code. This is what I want you to explore. Okay, at least during holidays, I want you to explore this. Okay, so I am just giving you so far in the lecture like tiny comments, and they are 1 or 2 liners. But at some point, you have to go into multiple liners in your Python. That's how you get a bit comfortable in writing codes. Okay, so now you can see the same thing we are doing. So data is given over here. Convert to pandas series. So pd.series data. So it's a pandas series. Number of bins equal to 4. Then apply pd.cut. Give the data like the series and the number of bins you want to perform the equal width binning, right? And that result you store in a data frame. So result is a data frame, right? Result is a data frame over here. You can see value we are giving, that is the S, and the bins. Okay, so this will tell you which value is going to which bin. Okay, fine. I don't want to discuss these parts because very new to some of you already. So this will come more in your data visualization. Okay, most what I'm trying to do over here is just plot a histogram. Just plot a histogram to show you that in equal width binning, the frequency of the number of observations in each bin is not the same. Okay, is not the same. So let us see. If you plot it, if you print it, you can see the value 5 will lie in this bin. The value 7 will lie in this bin. Okay, I hope it is kind of clear to last. So value 9 will fall under this bin, like that. So which value falls under which bin? Okay, that already pd.cut has done for you. This is not being done manually. pd.cut has already done this for you. Okay. And you can see bin counts, like you can also count how many elements are there in each of your bin, right? So you can see in this bin 44.9 to 27.5, you have around 7 values. Okay. In the second one, you have around 5 values. Okay. And 4, 4, right? So you can see number of observations are different in each bin. Okay, even though the width of each pin is the same. Width of each pin is the same, but the number of elements in each pin is different, right? So how, if I want to understand how the frequency is varying, so I can plot a histogram. Okay, for each bin, how many elements are there? So for each bin will be on the x-axis, number of elements or frequency will be on the y-axis. Okay, so like that you can plot an histogram over here. This is data visualization. It will come more in data visualization. No need to worry. Like it's simple. You have to import matplotlib as PLT, and then you have to do plt.hist for histogram. Okay, so no need to worry more about it. Just understand the basic idea what you gain from this figure. Okay, so it tells you that these are the data values, and in between 4 to what was our thing, 4.9 to 27.5. Okay, so 4.9, you see it doesn't start from 0, it starts from somewhere here. This is 4.9. Okay, 27.5 somewhere here. You can see here somewhere 27.5, and in between that, how many elements are lying? You can see 7. Okay, so this gives you the frequency over here. Okay, so you can see the peaks are not at the same level. The peaks are not at the same level. What does it mean? It means the frequencies are different. Okay, so in equal width binning, your frequency doesn't have to be the same, it can be different. So you can see the first bin has the largest number of observations, the second bin has the second largest set of observations, the last bin has the last set of observations. Okay, so yeah, and that is the idea. Anyway, so this is another humanized data, what we see over here. So what we can see is city. Okay, so I'm trying to. This is why I asked in Kochi, does it rain much or not? But I came to know it doesn't rain much. So this is just a synthetic data set, not a realistic one. Okay, so you can see over here this is a monthly rainfall in for some Indian cities. So I have considered this city over here, monthly rainfall, fine, and I am converting this to a data frame. Okay, how it looks like, you can print it. It looks like this. Okay, it tells you Mumbai has around 500 Okay, and Kochi has around 450. Ahmedabad has around 220 something like that. Now I want to bin them. I want to bin this data according to the highest, lowest, medium amount of rainfall. Okay, is it okay? Like we divided or we binned ages, right? Teen, adult, young adults. Then what comes? Middle, middle, seniors. Yeah. So therefore, there are 4 sets. So similarly, here also I want to categorize. I want to categorize. I want to bin which one? I want to bin this to medium rainfall, highest rainfall, lowest rainfall. So tell me, there are 2 columns. Which one we should bin? Should we bin the cities? No, you should bin the quantity, the numerical variables, the rainfall. So that based on the value of the rainfall, you will classify it as high or low, right? So maybe in your finals, you might get these kind of questions like to explore. You can have this data set, and the first question can be, you want to perform, like you want to discretize the data given to you, which method you should adopt. Okay, so you can say yes, we have to, and why you have to adopt. Okay, then the answer will be yes, we have to adopt binning strategy because it converts continuous variable to a discrete variable. Okay, and binning, we have to apply to which column, first or second column, second column, right? So I mean, very bit of insider things will be asked, so you should be knowing about a bit of things here and there. Okay, fine. So okay, so let us see how it has been. So how many, you can see there are 10 10 data values or 10 cities whose rainfall is recorded over here. Okay, and I want 3 bins, low, medium, high. Low rainfall, medium rainfall, high rainfall. Okay, so what do I should do? So you can see pd.cut I am applying, but I am applying only to the monthly rainfall column. You can see df stores this whole columns like city and rainfall, monthly rainfall data. But what I want to do is I want to extract only the numerical variable column, that is which column? Monthly rainfall okay, that way I want to extract. So I want to apply binning onto that column. So I provided input to pd.cut that sort of column, okay, not the cities column, okay. Fine. Bins equal to num bins. So I'm telling three bins you have to classify this data set into. Okay. And what are those bins? What are those bins? Those bins label. We are giving a label to the bins. Okay. Here you can give label to the bins also. Okay. What bin label I'm giving you over here? Low, medium, and high. Okay. So then I am trying to store it. So you can see the rainfall category. I have created another column over here in the data frame, which is rainfall category, and it will bin each of these value of the rainfall in into low, medium, or high. Okay. So you can see based on that, you can see 500 is categorized as high, 230 medium, 350 high, like that. So you can see where binning can be used. I mean, binning can seem to be a very intuitive concept, but you can apply it to many different data set based on your needs. Like you can see, like if you have a bigger data set of all the cities in India, and what you want to do is like classify the rainfall into high rainfall, medium rainfall, low rainfall, then binning is your particular method to go. Okay, so you can apply binning over here. So there are many things like that. You can apply binning to maybe any examples you can give where you can apply binning? Any example apart from this example, rainfall and age, which I already gave. I gave you two set of example. One is age and another is rainfall data. Anywhere else you can apply binning? Grades, yes. One of the very nice things about grades. So there you will have lot of binning labels. Grade O, that's the excellent grade. Sorry, grade A plus, which is the next one. A, B plus B, so many things. So imagine the same thing, like your class is about 100 students and we have to bin your marks. Okay, I will not bin according to your names. I will bin according to your marks, right? So binning according to your marks, then how we can bin? We have to bin, you can follow anyone, equal width or equal frequency, okay? But you have to check there are no outliers. So outliers means many of them have, how outliers can occur in your marks? Yeah, someone is scored like full, okay, and others scored like maybe very poor. So all are in one cluster, whereas one guy or one person is far away, right? Or maybe one person is there who did not write anything. So that is also a, I mean, outlier over there. So I hope that won't happen. Okay. Anyway, yeah. So here, the same thing I am doing over here, the same histogram. Here I am trying to plot how many cities are in the medium range, how many cities are in the highest amount of rainfall, how many cities are in the lowest amount of rainfall, right? So you can see the number of cities around 6, okay? Who has the lowest amount of rainfall is around 6. And the cities who have highest amount of rainfall is 3 and medium around 1, okay? Okay, fine. So the same thing I can show you for equal frequency binning. Take this data set, it's very synthetic data set, just for your example. And what I do is I apply Q-cut. So we want to divide this data into 4 quantile bins, okay, 4 quantile bins. And if you want to perform it like frequency binning or quantile binning, you have to apply Q-cut. Okay, Q-cut means quantile cut. So why we are referring about quantiles and all? Try to think. Okay, I already told you like what is first quantile, what is the difference between quantile and quartile. So these kind of things, these are some of your tiny tasks at home. So please note them down and try to explore this. Okay, what is quantile and what is quartile? Okay, what's the difference between a quantile and a quartile? Okay, so these are obvious, like these anyone can ask you. Okay, so you have to be ready. Anyway, so same thing over here, same thing, like data you are passing the array and q equals to 4. You need 4 quantile bins over here. Okay, fine. And what you do, you can see again, this one will be a series, pandas series, and that you are converting to a list using .toList. Same we did for your equal width binning. Okay, so you can see this is the Q cut. Okay, so what does this is your data. This you can see the output over here. I am printing the data set. Then I am printing bin labels Q cut. So it is telling you that this 7 means the first value, that is 7 over here, will lie in the first bin. Okay, 15 will also lie in the first bin. 36 will also lie in the first bin. Okay, whereas your 40 element will lie in the second bin. 41st second bin. 42nd third bin. 43rd again third bin. 47th fourth bin. Okay, oh, 3 3 6 3 9 10. 3 3 6 3 9 10. Are there 10 elements here? There are 10 elements, right? So each element of your data set, below it tells you which bin it will go. Okay, understood that, no? So it returns the index of the bin it will go. It returns the index, it returns the index of the bin it will go. Okay, fine. So you can see the number of elements in your data matches with the bin labels, number of bin labels. So there are 10 data values over here, and there are 10 values in your bin labels also. Okay, so this kind of tells you that where 7 will go. 7 will go to the first bin. Okay, and suppose where 49th will go. 49th will go to the fourth bin. Why I am telling fourth bin? Because it starts from 0. Okay, fine. So anyway, and if you plot, like, let us go, I won't discuss this this big code, but I made this code only for to give you an idea about the frequency. Okay, so same data set I have taken, the same data set. Okay, I have taken the same data set and I applied both equal width binning and equal frequency binning, and I am plotting the histogram of them. Okay, so you can see first is the equal width. For equal width, you can see that the frequency changes abruptly. Frequency changes abruptly, right? But for equal frequency binning, you can see the same amount, same number, but the number of elements in each bin is almost the same. So you get like a rectangular shape, almost rectangular. It's not perfectly rectangular, like perfectly same number of frequency elements, but there is, you can see, tiny bit of jump here. Okay, where it is almost the same, almost the same. Anyway, so last class I forgot to mention how to handle skewed data. I think some of them asked. Some of them asked how to handle skewed data, and I forgot to mention that in the class. So that we will hear it today. Okay. How to handle, how to manage skewed data. Okay. So I hope binning was a bit easier to understand. Okay, so far. You understood binning part? What is binning? Okay, you convert continuous to discrete set of variables. You understood. We will do a recap of 2-3 minutes. So we understood the different types of binning. We understood that there is something known as equal width binning. There is something known as equal frequency binning. Okay, also known as quantile binning, right? So then what happens in equal width binning? You make the width of each bin same. Okay, it doesn't matter in equal width binning, it doesn't matter how many elements are there in each of your bins. Whereas in equal frequency binning, you don't worry about the bin width, but you worry about the number of elements or observation in each bin. Okay, and how to perform equal width binning using pandas? You have to use pd.cut. And how to use like equal frequency binning in pandas? You have to use pd.cut. Q-cut. Okay, so the amount of like the input you have to pass is almost the same, but I asked you what does the labels means in that case. What does it mean? Labels equal to true, labels equal to false. Okay, so that you have to explore a bit. So go to Google and type pd.cut, what it can do for me, and what is the input. So what is the output of pd.cut? Yes, it will be a series. It will be a series of bin edges. I mean the Yes, yes. So the in each interval the maximum value, that is known as the bin edge. Okay, edge part of each interval. Those will be your output, and that will be a series. That will be a pandas series. Okay, And we can print how the series looks like. I gave you an example. It comes with index. Okay. So to visualize it better, we performed like to convert to a list. How we did that? We used dot to list. Okay. So of course there is no harm in printing the series. You will learn in your other course that you can perform the same amount of operations in both series and list. You can perform the mean, you can perform the median, maximum, minimum, all sort of arithmetic operations in like series. Okay, you have more scope in series. However, in list also you can do that. Okay, it depends. But you are in, since you are working in pandas, it is better to transform them into series. Okay. Anyway. So let us see into skewed data now. Okay. So you can see we last class we learned what is skewed data. Okay. When we call data to be skewed, and there was some argument and assignments also. Okay. So 3 assignments were given. Okay. We'll see. We'll see that. So when you call it a right skewed data, when you call it a left skewed data, and what's the relation between mean, median, mode in all of the cases, right? So, okay. So many machine learning algorithms such as linear regression, logistic regression, you will learn in next semester. Okay. And many clustering algorithms like k-means assume that your data is kind of normally distributed. So maybe in next semester, maybe both of your batches like DACS and CSDA will learn about gradient descent in different courses. So what does gradient descent do? Okay, gradient descent helps you to reach to an optimum value. Okay, gradient descent, that's a method. Gradient descent using gradient, it's a very powerful method, but it's not an all-in-all method that you will learn in next semester. That there are better methods than gradient descent. Okay, there are many methods like stochastic gradient descent and mini batch stochastic gradient descent, where you use parallel processing and put them into different batches. Okay, that DACS will be learning in numerical methods if I take, and CSDA will be learning in their predictive and those things. But anyway, so they perform gradient descent perform better when your data is normally distributed. So when you have a skewed data, then you face a problem. Okay, then you face a problem, and you generally have a skewed data when you take exponential data sets, where suddenly the data rises. Okay, exponentially. So there you will get some skewed data set. Now, how to handle those things? Of course, one of the ways I told you is like if you have some 10 to the power 5 value, if you apply log to it, it just transforms to 5. So it's got scaled down. It gets scaled down, right? So therefore, you can see these are the methods you can use. You can use something known as log transformation, right? You can apply the log transformation, and of course, some assumptions are there. Your data cannot be negative because log is not defined for negative numbers. It doesn't mean log of minus 10 to the 5 is not making any sense. Okay, because the input given to log will should always be positive, right? So you can see it reduces right skew data that we saw. If you take log 10 to the power 5, it gives you just 5 if the base 10. Okay, not defined for 0 and negative values. You can see some of the data like biological data and income data. Usually you can apply this sort of techniques. I have seen, like, I have not applied too much of biological data, but I have seen many of my friends from life sciences who always came to me asking about the log function and how to transform them. Okay, so I remember that it is useful in life sciences also. So you can also apply the square root transformation, like y equals to root x. So square root also transforms. Like if you have 10 to the power 4 and you take a square root, it transforms to 10 to the power 2. So you can see how nicely it scales your data. So there are other transformations like box transformations, Johnson's transformation. So you can, just for your, knowledge sake, you don't have to uh, memorize or do something about this. Just to tell you that there are some transformations which you can apply to skewed data and manage your skewed data. Because I told in the last class how to manage outliers, but I did not tell you about how to manage skewed data. Okay, so if you want to manage, these are some transformations you can use. So you can see log, square root, and reciprocal are simpler transformations. Okay, reciprocal is one of the best intuitive ideas, right? So how you can do 10 to the power 2, if you have 1 by 10 to the power 2 is 0.01. So suddenly 100 value you transform to 0.01, which is quite nice. You nicely have scaled. So this transformation is also powerful, but only you can give input as positive data. Okay, like if you have log transformations also. But this is quite interesting. This method quite interesting. Yo Johnson transformation, which can handle both of your positive and negative values. Okay, maybe this can be asked. Like, can you name a method which can handle both positive and negative skewed data? Okay, so what is skewness and what is outliers and how you manage both of them can definitely be a question. So you can write some of the methods. So anyway, so what's the plan here? Okay, shall we take a break? Needed. Okay, we'll take a break and 15 minutes. Okay, so we'll come back and we'll start with the feature scaling. What do you mean by feature scaling?